Okay, welcome students. I'm coming back to you with a video after quite some time. And during this time, I had posted some materials in your Google Classroom, and they were dealing with the divergence, gradient, divergence, curl, then the Gauss's theorem, Stokes theorem, and Green's theorem. So, as I have already mentioned in your classroom in the comment section, these theorems you need not study the proofs as mentioned in the syllabus. You just have to know what these theorems are all about, the statement of these theorems, and their applications. So at best you will be asked what is or give the statement of Gauss's theorem, and you may be given one or two problems applying that theorem. So before that, these are some things probably which you have not done in your higher secondary class. So I want to discuss a few points about the topics that I have posted in your classrooms. The del operator. This is something probably which you have not studied in your higher secondary. In your higher secondary, what you have studied is probably differentiation, and you have been talking about the derivative. So what it is, if you remember, differentiation is the process of finding out the derivative of what? Derivative of a function. So what is a function? Function is nothing but something of the kind having two variables, one dependent variable, one independent variable. Y is a dependent variable. It varies with x, so we call it y is a function of x. Or simply let us put it, phi is a variable which is a function of x. So this function, this variable rather, phi, it varies with x. So how it varies with x, or what is the rate of change of phi with x? How can we find out? We can find out by operating on phi by an operator we call d dx an operator. D dx is an operator which operates on phi, and the result that we get is the derivative. This should be clear. D dx is the operator which operates on phi to give us the derivative. So this phi, as we can see here, is single dimension. It varies only with one variable x. So in general, we can have functions which vary with, let me say, phi is a function which depends upon all three x, y, z in Cartesian coordinates. Let us say that phi is a variable which depends upon all three coordinates x, y, and z. So by now, all of you must have known this del operator. We write it as del is equal to I del x plus j del y plus k del z. So if I have a function which is single dimensional, then when del operates on that function, we get nothing but what is called the one-dimensional derivative. So del is a three-dimensional operator. It operates on the function to give us what? To give us the derivative. Three-dimensional derivative, generalized higher dimension derivative. Okay, so this del operator can operate on a scalar function. It can operate on a scalar function to give us the gradient of the scalar. So what is the scalar function? A function means a quantity which keeps on changing we are talking about a function. What is a function? It represents a quantity which keeps on varying with the coordinates. Let us say in the corner of a room I have a heater. This is winter, so we'll be putting on the heaters. In the corner of a room I put on the heater. So if I use a thermometer to determine the temperature of the room, depending on the location of the thermometer or the position where you measure the temperature, it will vary. So in the corner of the room the heater is there, so that is the origin. So as I change the coordinates x, y, z, as I move away from the heater in different directions, the temperature will vary. So here we can say that the temperature function is a function of x, y, and z. So what is the gradient? The gradient of any function. This is the temperature T we are talking about. Let us take this function that we talked about, phi x, y, z in general. So the gradient of this function is the operator del operating on the function phi. So that gives you the gradient. So this gradient is a vector quantity. You have to keep this in mind. This is a vector quantity. So what is del? We talked about it. It's I del x plus j del y plus k del z operating on phi x y z. So when it operates on this implies this will be equal to I del phi del x plus j del phi del y plus k del phi del z. I have already given you some problems where you have evaluated these gradients. So as I told you, gradient is a vector quantity. So what is the physical significance of this gradient? Any function, the gradient gives us the maximum rate of maximum rate of change maximum rate of change of the function. Okay, it gives you the maximum rate of change of the function, and as because it is a vector, it will have a direction. What is the direction of this gradient? The direction of the gradient is the direction in which the function changes the maximum, or the direction along which if we move there will be maximum change of the function. For example, the temperature I was talking about. So let us say this is a three-dimensional coordinate system. This is the origin, the corner of the room I was talking about. Let us put the heater here. Say this is the heater. So as I move along in different directions, I can move in this direction, and I can move in this direction, I can move in this direction with the thermometer. I can measure the temperature T1 here, I can measure T2 here, I can measure T3 here. So what it means, if I change the coordinates x, y, z, the value will change. Along different directions, the rate of change will be different. So you can imagine if your heater is glowing in this direction, maximum change will be along this direction. If you move parallel to the floor, change might be less. So this direction of maximum change is the direction of the gradient, and the magnitude of that maximum change, that is the magnitude of the gradient. So this is the physical meaning of, or the physical significance of, the gradient. Okay, then that is gradient. What about the divergence of a vector function? So divergence of a vector function, we talk about the function now. What is a vector function? Vector function is again a quantity which is a vector, but it changes as we change the coordinates. So instead of temperature, which is a scalar quantity, if I imagine, let me say at the origin of the coordinate system there is a charge. So this charge, it's positive, let me say. So this positive charge will have its electric field which goes out like this, radially. right? So how do we measure this electric field? We measure it by the electric field intensity, E. So the electric field intensity not only has a magnitude, it has a direction. So this is a vector. So it changes with the coordinates x, y, z. So we can call it a vector function. And the region of space around the charge where this electric field or the vector will have a value is known as the vector field. Any vector, it can be true for other vectors also. Now, what is the divergence of a vector function? If any vector function is there which has a finite divergence, diverge means how much it goes out from a point. You can imagine in your garden when you water the plants, the garden hose for watering the plants, the water gushes out from the jet. So it diverges out. So how can you measure how much is the water diverging from the tip of the hose? You can measure the divergence of the velocity vector. Here, how much is the electric field diverging out from this point? We can measure the divergence of the electric field. How is it measured? We call it the divergence of the electric field. Divergence. So divergence of a vector function is given by the dot product of the del operator and the vector. So in general, we can write it, let me say, I have a vector A which is having three-dimensional components along all three axes, AXI plus AYJ plus AZK. Then the divergence of this vector will be del dot of A. So that is equal to I, this is the del operator, I del x plus J del y plus K del z dot product with A xi plus a yj plus a zk. So when it operates, you know from the rules of dot products, I dot I is 1, I dot j is 0, I dot k is 0. So only I dot I, j dot j and k dot k terms will remain, the others will vanish, will become 0. So this is del ax, del x plus del ay, del y plus del az, del z. So what is this divergence? Is this value. What is the physical significance of this divergence? And you can make out the divergence is always a scalar. It's always a scalar because the dot products gives us a scalar. Unlike the gradient, which is a vector. Divergence is a scalar. So what is the divergence? It will have only its magnitude. The magnitude of the divergence of a vector quantity gives us the amount by which the vector field diverges at that point where we are measuring it. Let me say I take this point which has the coordinates x1, y1, z1. So for the electric field, I can find out for this point, let me say this is the point P1. So at this point, we can find out the divergence of the electric field at the point P1. What we have to do, we have to just find out, del dot T, the result that we'll get, we have to substitute the values of x1, y1, z1. We have to substitute x is equal to x1, y is equal to y1, and z is equal to z1. What it will give me? It will give me the amount by which the field diverges out from this point. So that is the physical meaning of divergence. So if I have a field which does not diverge, which comes back. Any example you remember is the magnetic field. Magnetic field is something like I have a bar magnet, north and south. The field lines, they go out and they always come back. They go out and they always come back. However far it goes, it will always come back. So this means what? This field, they don't diverge. So if I find out the magnetic field, if I find out the divergence of that field, invariably we will get it as 0. So that's it, give you an idea about the physical significance of the divergence. Okay, next we come to the curl of a vector field. What is the curl of a vector field? The significance you can make out from the name itself. How much a vector field it curls round a point. Curling vectors. Just now we talked about the magnetic field. The field lines, they curl, they go round. Similarly, if you wash utensils in your basin, when you pour water, you'll see that a vortex is formed. The water curls round and goes in. The velocity vector for the water will have a finite curl. It's curling round a point. So curl of a vector field or a vector, it determines the magnitude of the curl. It determines how much a field or a vector is curling round a point. So in the case of the magnetic field, we can find out the curl. So how do we find out the curl? The curl is found out by finding the cross product of the del operator with the vector. Let me say A. So that is I del x plus j del y plus k del z cross product with axi plus of ayj plus of az of k. So this is nothing but equal to the determinant. So ijk del x del y del z ax ay az. So given any vector, you can always find out the curl of the vector. Here field, you may or may not remember, we can talk about the curl of a vector. So what is the physical significance? Again, I told you. The physical significance of the curl of a vector determines how much the vector turns round a point. So you should be able to make out for an electric field, the field lines, they are straight. They go out radially from the charge. They are straight lines going out from the charge like this. So if I find out the curl of the electric field, you should be able to tell me now, as because it is straight, at any point they don't go round. So for the electric field, the curl of the electric field, in this case, it should not exist. There is no curl. It doesn't curl. It should be equal to 0. But for a magnetic field, there is finite curl. So that is the significance of the curl of a vector field. Next, we talk about the line integral. We talked about the surface integral. We talked about the volume integral. What it is? I've given you notes on this. Line integral, you can make out, it's an integration taking place along a line or a curve. So how many variables will be there? Say something is moving along a curve. So we'll be talking about only displacement along the curve. So that becomes a line integral. We integrate any function, let me say phi, it can be x, y, z. We'll call it dl integration over, we do it like this, over the curve, or we can put a c over here. So what is dl? Dl is an element of length. So what changes? As we move along the line, dl changes. So as dl changes, phi. So this is, we call it a line integral. Okay, what is a surface integral? You can imagine an ant moving on the line. What is changing is only its displacement along the line. It can't move out any other way. So only one variable is changing, is the displacement along the path or the line or the curve. This is a line integral. What is a surface integral? Same thing, you can imagine an ant moving on the surface of this paper that I am taking. If the ant is moving along this direction like this, somewhat like this. So what changes? Two variable changes along the surface. So surface, let me say this is x-axis, this is y-axis. So it will have two variables. So if an ant moves from this point to this point, infinitesimally small distance, okay, the displacement along this dl can be denoted as I dx plus j dy. So both x and y will change. So when integration is done over a surface, that is known as surface integral. We call it, so it is two-dimensional. You can either denote it like this. Let me say I have phi xyz. So this is, integration is done over a surface where surface is equal to dx dy. Element of the surface is dx dy. And for that matter, surface area is always a vector quantity. If I have to denote a surface, a unit vector perpendicular to the surface can denote its direction. Direction of what? Direction of the surface. So for this surface, the unit vector will be perpendicular to this, like this, going up. Right, so surface can be denoted as dx dy. So in this case, if I take this as I, x-axis, y-axis, so it will be along k. So this is a surface. So it has two variables. So surface integral, probably you have been talking about the flux of an electric field in higher secondary. The flux we talk about, right? So that is F dot ds or E dot ds, electric field dot ds. Or in other words, surface integral involves two variables. We are talking about, here is a function x, y, z. Then we have two variables dx, dy. Or we can write it integration over, one stands for x, the other stands for y, and two variables here. For volume integral, what happens? Volume integral, it becomes three-dimensional. Three-dimensional, so integration over volume 3 x, y, z. So phi x, y, z dv. So what is dv? dv is an element of volume. So if I consider in three dimensions, it's something like this, right? So dv is a small element of volume here. So what are this? Let me say this is x, this is y, and this is z, or you can call it, so x, y, and okay, let this be x, let this be y, let's be consistent. So this is x, y, and z. So change, small change along this is dy, okay, this is dx, and this is dz. So a small element of volume in Cartesian coordinate system, dv is equal to dx, dy, dz. So the volume integral will be integration over x, integration over y, integration over z, phi, x, y, z, dv is dx, dy, dz. So line integral is one dimension. Surface integral, it involves one variable, one dimension. Surface integral involves two variables. Volume integral involves three variables. So which one will be the easiest as such? If you look into it, obviously the single variable one should be the easiest. Two variables, bit more complex. Three variables, most complex of all. It's like dealing with people. If you have to deal with one person, it's easy. Two persons, a bit difficult. Three persons, a bit more difficult. A crude example. Now, what are these theorems that we talked about? One is Gauss's theorem, and the other is Stokes' theorem. Green's theorem are just corollary to this. Using these two theorems, we get the Green's theorem. But what is Gauss's theorem? Gauss's theorem, what is the significance? I won't write the statement of the theorem, it's there in your notes. But what it does basically, it converts a three-dimensional or three-variable, volume integral to a two-variable surface integral. Of course, certain conditions needs to be satisfied. Under certain conditions, the Gauss's theorem gives us a tool. It is nothing but, both these theorems are nothing but tools. Why do we use a tool? We use a tool to make our work simpler. If I have to cut something, I will use a blade, I'll use a cutter. Instead of tearing with my hand or with my teeth, it will be always easier to use a tool. So these theorems are nothing but tools. Gauss's theorem is a tool which can be used to convert a three-variable volume integral into a two-variable surface integral. And what is the Stokes theorem? The Stokes theorem gives us a tool to convert a two-variable surface integral to a one-variable line integral. So that is the beauty about these two theorems. It simplifies our job. Application-wise, I had given you already few solved problems on all these: line integral, surface integral, volume integral, then application of Gauss's theorem, Stokes' theorem, and even the Green's theorem proofs I have given. So basically, these theorems are nothing but mathematical tools. I can't compare with the cutter. These are tools of mathematics, which makes our calculations easier. So whatever was posted in the materials, whatever I had given in the materials, those are not all. Many books are there, many resources are there in the net. You can download, you can solve more problems on these topics. And you need to remember the statement of these theorems. What is Gauss's theorem, what is Stokes' theorem, and the statement of the Green's theorem. And of course, you need to know how to apply them. Okay then, that's all for today.